All right. Well, last time, do you remember what we did last time? We actually solved the critical section problem completely in software by analyzing a lot of, what we did is we analyzed a lot of failed attempts, but eventually we had, I think, didn't we have like 4 different attempts? I think we had first attempt, second attempt, third attempt, fourth attempt. And then finally, the last attempt is, in fact, what is known as Decker's algorithm, in which, and here's the code for it. You remember we ended with this. And let's review a little bit the idea behind Decker's algorithm. The idea is that we have 2 Boolean variables that are globally accessed by the running processes, P and Q. The first one is want P, and the second one is want Q. And why do we call it want P? Because P wants to get into its critical section. That's the purpose. That's why we call it want P. And now, and if want Q is true, then Q wants to get into its critical section. So P sets want P and Q sets want Q. But P tests want Q and Q tests want P. Are you with me? Do you see how that interaction happens? And not only that, but in addition to this, we have another variable called turn. And turn is not Boolean, it's a number. And do you remember what does turn indicate in Decker's algorithm?
Whose turn it is to insist that the other go in? Or
It is. But turn only comes into play if they're both what?
They both want to.
If they both want to do what? To enter at the same time. In other words, if they're both in their pre-protocol. Then what happens is, if they're both in their pre-protocol, then instead of having them duke it out, you see what I mean? Which might cause starvation, if it's spinning around. Then we will, we will take turns. But taking the turns only comes into play if they're both in their pre-protocol at the same time. You see what I mean? So if one of them is not in its pre-protocol, if one of them is in its non-critical section, even if it's the other person's turn, that won't come into play. The other one can keep going in and out, in and out, in and out of its critical section. That's the idea. Does everybody see the idea? It's really a nice idea. Okay? But the code is a little complicated, and we haven't proved this. The entire next chapter is proving the correctness of Decker's algorithm. So we're going to have to learn some linear temporal logic, actually, to do that. So, but this is the code. So P has a non-critical section, and then the pre-protocol is P2, P3, P4, P5, P6, and P7. That's all the pre-protocol. So want P gets true, so he's announcing his intention he wants to get into his critical section. And then, but if Q is there, then he goes into this loop at P3. But if Q is not wanting to enter, it's possible for the body of the while to never execute at P3, in which case the next statement could be P8. Are you with me on that? But even if there's interleaving after P3, so if P3 tests Q, which means the next one's going to be P8, even if there's interleaving before P8 executes, this is guaranteed, even if there's interleaving, this is guaranteed to let him in without the other guy getting into his critical section. Are you with me? You see how all those issues are resolved by this code, all those issues. And then on the other hand, if want Q is also true, now then what happens is he has to do this, the body of this while loop, and the body of this while loop has an if turn equals 2. So if it's the other person's turn to insist on going in, then he has to execute this await, right? And this await, how did we say we implement the await statement? With what kind of what's the programming technique? It's a loop, and what are those loops called to implement the await? They're called what? They're called spin locks. And it is a while. The spin lock is that's correct. A spin lock is a while loop. And it basically just spins. And what is its purpose? It just spins consuming cycles until what event happens? Until what event happens? A spin lock delays by spinning in a loop until what happens?
Until it fails.
Well, those are all true. Those are all true in a sense, but the spin lock physically in the system, the spin lock wastes time by looping
until it times out.
Until a timeout. Yes, until a timeout. Now everybody understands the concept of a timeout, right? What happens is the operating system, when it puts a process in there, it puts it in there and sets an alarm clock. And it only gets a time slice. And then after that slice, then another one gets in. Now that is that is a model for a multi-what? If there's one processor, and they keep getting switched in and out by multi-programming system. If it's a multi-processing and it's looping there, then the other one could be physically looping at the same time with its CPU, with its core. So it could be spinning in one core and the other one spinning in its other core. In that case, then not necessarily a timeout, but what? Well, no, hopefully it's not deadlock. Hopefully it's not deadlock. Well, no, if they're both spinning, it might not be because of a timeout. It might be because what? The other one sets turn to 1. And then when the other one sets turn to 1, then if it's spinning there even before timeout, then it will make progress after the await. Then it will execute P7. So everybody see how that works? But we know that logically, what do we know about the multi-programming versus multi-processing systems? They're logically equivalent. So regardless of whether we think of this as spinning until a timeout or spinning until the other guy the process sets turn to 1, it's the same logical. They're logically equivalent. Yeah.
Would it be really bad to just have it so that if they are both trying to get in, just having it so P always goes first?
That was our very first attempt. Oh, so it always goes first.
Right.
Oh, well then there's a high chance of starvation.
Okay.
Yeah, but see, our very first attempt was to take turns actually getting in. Here, we aren't taking turns getting in, we're taking turns if they both want to get in at the same time.
Yeah, I guess I was thinking like having a want P but no want Q, so Q just won't go in.
Yeah, but that's highly unfair, and I think you're subject to starvation.
Okay.
Yeah, I'm pretty sure that's what would happen. Okay, so does everybody see? Now what we're going to do, so this is a review of Decker's algorithm. What we're going to do is we're going to do some logic. We're going to prove that it's correct. And the next whole chapter, chapter 4, is devoted to these things. Okay?
What if we have more than 2 processes?
Oh, that's a good question. How would you generalize? The question is, what if you have more than 2 processes? And all of these algorithms, we have to consider if they would work with 3 or 4 or 5, n processes, that's a very good question. So I will leave it to you to think about that. How do you generalize? And so there are exercises in the book that treat those for the different algorithms. All right, that's a good question. All right, now this next thing gets down to a little bit of a. We're going to get down to some hardware on this next little segment. Now, let's go back and look at Decker's algorithm. What kind of statements do we have in what kinds of statements do we have in Decker's algorithm? Well, first of all, what is P2? What kind of a statement is that? It's an assignment statement. We all know how assignment statements work, right? Load store, yeah? Are you with me? Okay. And what kind of a statement is P3? Well, I mean, it's not a spin lock. It's a loop, but it is a loop. It is spinning, you're right. I mean, in a sense, it's spinning, yeah. It's a loop. And what kind of statement is P4? It's an if statement. No, well, actually, P4 is not a loop. P4 is an if statement. It's an alternative statement, you know, like case or switch or whatever, okay? Okay, so we have statement. And then a more assignment statement, and then we have this await. Now, the await is implemented with the loop, but we can implement that with a loop, right? A spin lock, right? But now, one of the statements that C, and all these are C++. You can code this up in C++. Now, one kind of a statement that C++ does not have is a statement called test and set. But let's imagine that in fact C++ had this test and set instruction. All right? Now here is what the test and set instruction does. Test and set you give it two things. You give it two variables. Actually, you give it two variables. These are you give it two parameters. It's kind of like it's a statement that operates on two different things. Okay, a common and a local. And what it does is it does local gets common, and then common gets 1. That's a 1. Are you with me? But furthermore, it does it in one atomic. It does it in one atomic operation. Now, so that's called test and set. Now, do you see why it's called test and set? Because when it does local gets common, that's testing what common is, and when it does common gets 1, that's setting common. So you see why it's called test and set? The first one, local gets common, is, local is going to get common, so now my local has a copy of common. But at the same time, with no interleaving, I'm going to set common to 1. Common is an integer.
Wait, how is having local get common, how is that testing? Like, what is that?
I'll show you. See, it's testing it in that it's getting its operation. It's testing it in that it's setting a local to its value, so now it has it, and it can, now it has it. And then it's going to set common, and then it sets common to 1. So it gets its value and it sets it, but it's indivisible. The operation is indivisible. But you ask a good question. How is that testing it? Let's take a look at how it's used. But do you agree with me that, do you understand the semantics of this instruction? It's in one atomic operation, no interleaving. If in fact C++ or Java had an atomic test and set, then guess what? The critical section problem becomes trivial. And we wouldn't have to go through all of this Decker's algorithm stuff to do it. And here's what it would be. Here is how it would work. The critical section algorithm with test and set is this. You initialize common to 0. And then what you do in the pre-protocol, you repeatedly test and set until the local is 0. So you see what you do is you test the local after you do the test and set. So you repeatedly test and set until the local is 0. If common is initially 0, local will be set to 0, and the common will be to 1 in one atomic operation, and the process will enter its critical section. Now, are you with me on that? Mm-hmm. Okay. And then in the post protocol, it's just one assignment statement. You set common back to 0 so that the next process will be able to enter its critical section. So look, you guys, here is the code. Are you ready for this? Algorithm 3.11. Critical section problem with test and set. If there were a test and set, then here's what we could do. We could say have this integer common initialized to 0. All right? And then P has its integer local 1 and Q has its integer local 2. Right? And so we're going to loop these things forever. And we're going to do our non-critical section. And then is all we have to do for P2 is repeat test and set common local 1 until local 1 equals 0. Now, are you guys familiar with the, you should be familiar with the repeat statement as opposed to the while statement? Have you, in C++, does anybody know how to do, look, where is the test of this repeat statement? Is it at the beginning of the loop or is it at the end of the loop? It's at the end of the loop. Now, do you know how to write the test, C++ loop, where the test is at the end instead of at the beginning? Yeah, it's instead of saying while in C++, you do it, yeah, in C++ you say do. You say do. And then you do blah, 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 blah. And then down here you say while. Well, now here's while, yeah, let me see, how can I say that? While condition. And then you go on. Now, have you guys done this?
Where do you print the end break?
Here. Do all of this. So if you don't have the brace, you can just have one statement here. The brace is a compound statement. Okay? So if you don't have the brace, you can just have one statement here. But anyway, it's do and then while condition. But now, this is slightly different from the repeat because, I mean, this is how you would do it. So this is C++ and Java. So this is C++, Java. Now, this is a slightly different, because you do this while. So when do you keep doing this? When the condition is what? True. But the key word here isn't while. The key word here is what? Until. So how does this work? Until local equals. So if the condition is true here, if the condition at P3 is true, you go on and do P4. But here, if this condition is true, what do? You do this. So the condition is the opposite. But it's still, the main thing is the test is at the end of the loop. Now, is everybody clear on that? So if you have if you were to translate this to, C++, it would be do instead of repeat, and then instead of saying until local 1 equals 0, it would be what? Instead of until, while local 1 is not equal to 0. Yeah. Is everybody clear on how that works? Okay, so that's, some semantics, a little bit of difference between our pseudocode here and these actual languages. But, and there are some languages that actually use repeat until. I kind of like it better. I like repeat until. We repeat this until this, and then when that's true, you go on. Okay, but anyway, whatever. All right? And look, you guys, this solves the whole thing. Because look, what would happen? So suppose that P and Q are trying to get in at the same time. Well, the fact that this test and set is atomic means that only one of them can get in. Do you see what I mean? Only one of them can get in because there's no interleaving between the, there's no interleaving between the common gets, between the what? The local gets the common and the what? Common gets one. So just, Well, that's the problem. The problem is that to do this in a high-level language you can't, it's very difficult. To do this in a high-level language is very difficult. So no high-level languages actually have this equivalent. Is everybody clear on that, on how that works? And we can go through a little scenario here. So common is 0. So do you see that common is 0, right? And so suppose P1 executes and then Q1 executes. And then suppose P2 executes and does test and set. Now, if P2 executes and does test and set, what will happen? Common will get what? 1. All right? And then suppose, is everybody clear on that? Common will get 1. And then suppose after P2 executes, suppose Q2 executes. What will it do? It will repeat what? But now when it does test and set, what does it do? Yeah, but this is until local, this is until local 1, yeah, this is going to be until local 1 is what? 0. But this is until local 2 is 0. But what happened with local 2? It got 1. So this is going to keep spinning. So the first one who did the test and set is the one who's going to get in.
And this works for in process as well.
Yeah. Yeah. This is really cool. But it's very difficult at the high level, because see, compilers translate high-level languages into multiple loads and stores, and to do that assignment and stuff, it would have to do that atomically. But those happen at different cycles. I mean, you see what I'm saying? The compiler has to translate that. I mean, so it's not typically available in a high-level language. Now, actually, there's another way to do it. There's another. Not only can you do this a trivial solution with a test and set, but also these are called exchange statements. If high-level programming languages had atomic exchange statements, the critical section would be trivial. Now, what do we mean by an exchange? Like swap. What do we mean by swap?
Double assignment.
Yeah, I mean, yeah, AB gets BA or whatever. You swap the values. Right? So let's suppose that you could do exchange AB, and basically what it is integer temp gets A gets B gets temp. But now, what if you could do all of this in what? One atomic statement. Suppose you could guarantee that were atomic. If the exchange is guaranteed to be atomic, no interleaving. Well, if you have an exchange statement, then it's also trivial to solve the critical section problem. You initialize common to 1 and local to 0. And in the pre-protocol, you repeatedly exchange until the local is 1. If common is initially 1, local will be set to 1 and common to 0 in one atomic operation. And the process will enter the critical section. And then if the other one tries to get in, it won't. See, because you did the exchange. See? And the post protocol is you exchange the common with the local back again. So the next process will be able to enter its critical section. So here's the code, algorithm 3.12. It's repeat. So here, common integer, common gets 1. And we have a local variable, local 1 gets 0, local variable, local 2 gets 0 in Q. And then we have the non-critical section. And this time it's repeat, exchange common local 1 until local 1 equals 1.
Some architectures have
And yeah, well, you don't typically have this in a high level language, but here's the thing, you guys. Early on in the development of the computer hardware, because the very, very earliest, like back in the late 40s, the early 50s, I mean, there were no operating systems, and there wasn't any parallelism. You see what I mean? There wasn't. But then pretty soon they hooked up, they would hook up disk drive or tape drives and then disk drives, and pretty soon operating systems came along and they started to have parallel processing. And early on it was discovered, I mean, these problems, the concurrency problem, the critical section problem became evident. And early on in the development of computer hardware, this fact, this test and set stuff, it was recognized that this was a way to solve the critical section problem. So what happened was, what happens now, and from a very early stage, now what happens is these instructions are hardwired into a single machine language instruction. And they're guaranteed to be atomic. And the hardware can guarantee that they're atomic. Because these are actually part of the instruction set of a processor. And what I've taken here is I've extracted from the manual, the Intel manual, the instruction set reference of the Intel manual. And here is an example of test and set at the machine level for an Intel chip. And what it is now you guys have had computer systems. You have mnemonics. Okay, and it's the BTS instead of the LDA for load accumulator and STA for store accumulator. BTS stands for what? Bit, test, and set. And the purpose of them putting this instruction in, look, it even says, this is from the manual, This instruction can be used with a lock prefix to allow the instruction to be executed atomically. And the reason for it is so that at the hardware level you can do spin locks like that with atomic test and set. And not only that, here is an example of the ARM chip. You know how, have you heard of the ARM chip, ARM? It's the Advanced RISC Machine. There's probably more ARM chips than there are Intel chips, because ARM chips are the ones that are used in practically every mobile phone and mobile device. Your phone, I'm 99% sure that your phone has an ARM chip in it. Your phones don't run with Intel chips. They're too power, they require too much power. ARM was designed from the ground up to be a RISC chip that was low power. The A7 is an ARM. The A for the A7 for the Apple product is an ARM chip. And here's an example from the manual, of the ARM chip manual. Check it out. It's called what? So now what is this? SWP, which stands for what? Swap. And what it does is it takes, these two registers, it'll swap them. And here, RTL, oh, remember what RTL is? Oh, remember RTL from computer systems, what does it stand for? Register transfer language. There it is in the manual. Here's the register transfer language. Temp, arrow, blah, 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 blah. Flags updated, blah, blah, blah. And that's why they supply that. It's because it's guaranteed to be atomic. And so you can implement, it's like, that's what it's for. Are we good? Does everybody see how all that works? All right.
If they have those, why can't higher order languages do it? It's already built into it.
Well, you say, why don't they provide that at the high level language? Well, it only has a specialized use. High level languages are general purpose. And it just it's a specialized use. And not only that, you have to do it. It might depend on the register size. It might depend on the size of the data thing. It's of marginal value to the general purpose programmer at a high level of abstraction. At a high level of abstraction, we're going to use other design tools for doing concurrency at a high level. But for doing it at a low level of abstraction, that's what they're for. All right? Isn't that interesting? I think that's cool. All right. So now guess what you guys get now? Are you ready for this? Remember how in formal methods we had propositional calculus and predicate calculus, and then we had theory of sets and all blah, 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 blah? Well, guess what? This is a reprint of your propositional calculus plus linear temporal logic. And so you're actually going to use our proof techniques that we learned in formal methods. So, and this will be, and if I ask you to prove a theorem on the final, I'll give you a copy of this, so you don't have to memorize it, okay, as before, right? So do they look familiar? 3.8, definition of false. 3.16, symmetry of not equivalence. Disjunction, conjunction. Remember our old friend 3.59, implication? Remember that? Okay, so all of this stuff, page 1, 2, 3, 4, 5, Leibniz is an axiom, proof technique, edit theorems. Pages 1 through 5 are review from your formal methods course. What we're going to do is linear temporal logic, starting on page 6. Okay? So, here we go. Verification of concurrent programs. Processes? Programs. Verification of concurrent programs. Chapter 4. Now, our author, unfortunately, doesn't use the same system of logic that we learned in formal methods. He does not use this equational logic, But because we learned it that way, I have recast a lot of his arguments from English into our formal methods way of doing things, all right? Into our equational proof style. And I think this is really nice because we're actually using all of this stuff that we learned before in a different course, right? To study this. And it's very, I think it's very neat. It's a very nice application of what we learned. Okay, so here we go. What we're going to do is, our first use of this logic is in this chapter, we're going to see how to prove the certain characteristics of concurrent programs. The first one that we're going to look at is a proof of mutual exclusion of our third attempt. Now, do you remember how did those attempts go? The first attempt was take turns, and the second attempt was having a want P and a want Q, but it didn't have mutual exclusion, and then we flipped the order, and that was our third attempt. Do you remember that? And we did that third attempt to show that, so that we would have mutual exclusion. Now what we're going to do is we're going to prove mutual exclusion using logic instead of using the state, instead of doing an exhaustive rundown of the states, okay? So here is a reprint. This is algorithm 4.1, but it's a reprint of our third attempt. And let's remember how it worked. So we had Boolean want P gets false, want Q gets false. And then we had the non-critical section, and then want P gets true, because in P2, P wants to get in, so want P gets true. And then we do await want Q equals false, so that's our little spin lock where that's going to await. So if he's trying to get in, but then Q is trying to get in, so we do await want Q. And then the critical section and the want P. Now, and then the post protocol is want P gets false. This obviously has a flaw. Do you remember what the flaw was in our third attempt? Yeah. So we're just doing that. But what we're going to do is we're going to prove mutual exclusion for this, just so that we can see how to reason about concurrent programs using logic. Is everybody clear? All right. Now, first thing that we have to do is we have to do some notation. We have to learn some notation. And in this chapter, what we're going to do is this notation, P3.5. When we say P3.5, that means P3 or P4 or P5. And what does P3 or P4 or P5 mean as a Boolean expression? That means either statement P3 or P4 or P5 is the statement that will be executed next when process P is chosen. So does everybody see what that means? It's a disjunction. Are we good on that notation? Pretty simple notation. We don't want to have to write P3 or P4 or P5. We just do P3.5. All right? Okay. Now, the first thing that we're going to prove is this lemma 4.3. Lemma 4.3. By the way, these slides, I just uploaded these. I just uploaded this version of these slides a couple hours ago. So if you're using an old version, you might want to refresh your browser to get the latest version. Okay, so let's take a look at this lemma 4.3. It says P 3.5 equivals want P is invariant. Now let's think about what that means. First of all, what does it mean if you say P equivals Q? What does that mean? What does it mean to be equal? I mean, can we break that down? And it means that is correct. It means either they are both true or they are both false. That's precisely. Is everybody clear on that? So, and what this lemma is saying is that P 3.5 equivals want P is invariant. So what is, so that means either P3.5 is what? True, and what? Want P is true, want P is true. Or P3.5 is false, and want P is false. So that's what that means. But now what does it mean that it's invariant? It means that this thing is true where? If it's invariant, where is it true? Everywhere. What does everywhere mean? Regardless, you know, as these are executing concurrently, regardless of the state. Do you see what I'm saying? It means regardless of the state, that's true. That's invariant. Doesn't matter what state you go from one state, you go to another state, you go to another state. That's always true at every state. Do you see? P3.5 equivalence 1 is invariant. Okay? So now, the proof is by mathematical induction on the states, because look, where do we always start? Because in order for these things, when these things are running concurrently, where do we always start? At the what? At the, well, I mean, the programming, I mean, we start at, you know, if I were to draw a little oval for the state, what would I put for the, we would start at what? P1, Q1. We'd start at P1, Q1, and furthermore what? Yeah, well, it would be P1, Q1, false, false, for the values of want P and the values of want Q, right? Is everybody with me on that? And then it would evolve in time, and as it evolves in time, what we want to do is we want to prove that that's invariant. So it's proof by mathematical induction on the states, and the base case is the initial state. And then we have to analyze how can it make transitions. Now you see how we reasoned that out? Okay? So let's do the base case. Okay. The base case, so it's P3.5 equivalence want P. So now, what did we say the base case was?
The initial state.
Initial state, which is what? P. Well, no, it's P1, Q1, false, false, right? So tell me, what is P3.5? So here, the initial state is P1, Q1, false, false, right? So now tell me, can somebody tell me, what is P3.5 in that state? You are right, it is false. Why is it false? Because it's P1, because it's not P3 or P4 or P5. And what about want P? And yeah, right, because, okay, so therefore this is false or false or false equivalence false. But now what do we know about false or false or false equivalence false? What do we know about false or false or false? Okay, by what? Idempotency, look up your thing there, 3.26. Are we good? Idempotency, so that makes it what? False or false or false is false, right? Okay, so now what? What do you think? Which one? You got to quote it in your packet, in your handout, in your equation sheet. Are you just doing that from memory? 3 point. Well, look it up and figure it out. Look.
3.3.
Yeah, it is 3. Oh, I said 3. Well, maybe you could do it either way, right? Because 3.5 is P equals true.
No, that's 3.
Oh, sorry, I had it the other way around. But either one would work, right? I think that would work. Either way, we get it to true, right? So everybody see that that's how we do the base case. Now, it's a little trickier though. How are we going to do the induction case? How do we do the induction case? We assume that it's what? How do you do proof by mathematical induction? You assume it's what? True for some intermediate state, and then prove that if it's true for any intermediate state, it must be what? Well, no, not for all. No, that's...
Except for the base.
No. How does proof by mathematical induction work? Yeah, in the next one. Yeah, you prove that if it's true in one state, it has to be true in the next state. And then that, together with the base case, shows that it's true for all of them. All right, is everybody with me on that? Okay, so here's how we're going to do the reasoning. So here's the induction case. The inductive hypothesis is we assume A is true in any state, and then we prove that A has to be true in any subsequent state. So what we have to analyze is the transition from one state to another state. Is everybody with me on that? Okay, so here's what we do. Now, yeah, question?
Why is it any state instead of the first state?
No. Oh, why is it any state instead of the first state? No. The first state we proved, the base case, we proved it. We have to prove it that if it's true in any state, it's true in the subsequent state.
So you're
And-
for an abstract
S-
state.
Yeah, that's the way proof by mathematical induction. Remember, when we were proving like mathematical induction for like the sum of something, we would prove it for the base case, and then we said if it's true for n, prove that it's true for n minus 1 using n as the inductive hypothesis. Remember how that logic worked? Okay, so now what we have to say is we assume it's true for an arbitrary state, prove that it's true for another state. But look, how many states are there? Yeah, I mean, who knows? I mean, we'd have to go through and count all the states. So we have to use some reasoning to see. So what do we have to reason? What is it that we're trying to prove? We have to reason how that A, capital A, can change. Do you see what I mean? All right. So the question is this. Execution of which statements can change A? Execution of which statements can change P 3.5 equivals want P. Now, can you inspect the code and tell me which one of these statements? We're looking at the P side here, P 3.5 and want P. Which one of these statements can change this expression, P 3.5 equivals want P? Why can P2 change it? Because it's changing want P. That's a very good observation. Everybody hear that? P2 can change it, but what else can change it? Why can P5 change it? Because if we execute P5, what'll happen? It'll, oh, no. Oh, wait. Right, P5 will change want P. That's right. P2 will change want P, and P5 will change want P. Right? Yeah, this is a lemma that we're going to use in a later part of the proof. So the significance of it will have to come later. The question is, why are we proving P 3.5 equivals want P? This is a lemma, and we're going to use it in the later part of the proof. So now, does everybody see that by code inspection, only P2 and P5 change this? So notice here. So here's P2 and here's P5. But look, you guys, that's the only thing that can change it. But look, you guys. So let's take two cases. What does execution of P2 happen? When we execute P2, that makes what? If we execute P2, what does that make happen? That makes it. Well, if we execute P2, what does that do to P 3.5? It makes it true. Do you see what I mean? Because what is P 3.5? It's P3 or P4 or P5. So if P2 executes, then we have P3, which means P 3.5 is true. Are you with me? But it also does what? Execution of P2 also does what? Yes, it makes want P true. So A becomes what? True equivals true. But what do you know about true equivals true? That's true. Because P 3.5 means P3 or P4 or P5. So if P3 is true, it doesn't matter about P4 and P5. They're false. True or false is true. No, but P3 or P4 or P5 is true. Are you with me? Look. P3.5 equivals P3 or P4 or P5. So what I'm saying is that it makes P3 true. When you execute P2, that makes P3 true. You with me? Because that's the statement that's going to be executed next. So what that makes this is, that makes this true or false, but this is true, we know from predicate. Are we good? You see how that worked? Okay. So, but on the other hand, it not only does it make that true, but it also sets want P to true. So we have true, which means true. Now what about the other one? The other one was what? P5? But now what about this? If we execute P5, what does that make happen? Yeah, P3.5 false, but it also makes what? On P false. So what? It's false equals false. So by mathematical induction, what do we know? P3.5 equals want P is invariant. And similarly, we could just a mirror case, right? Q3.5 equals want Q is invariant. Are you with me on that? Okay, so now, Chloe, check this out. We're going to be able to finish this. Watch this. Theorem 4.4. Not P4 and Q4 is invariant. Now, what are we proving here? They can't both be in their critical section at the same time because P4 is the line for the critical section. So if we can prove not P4 and Q4, we have proved, logically, we have proved what? 4.1 ensures mutual exclusion. But look, how do we prove that anything is invariant? How do we prove anything is invariant? Mathematical induction. So what do we have? First, the base case, okay? Proof by mathematical induction. So here's the base case. Not P4 and Q4, okay? Equals, by the base, the initial state is P1, Q1, false, false. So what is that? So what do we have for P4 and Q4? False and false. So we have not false and false, but what do we know about false and false? By what? Equation sheet? I think we can use item potency, right? Or zero of and. Okay, I think I use item potency. Is everybody with me on 326? So by 326, what is this? Well, not false. Okay, so look it up. Give me the next number. Come on, look it up. Look it up. Say it again. Okay, 3.13, true. Okay, and now what about the induction case? Assume what? P4 and Q4 is true in what? In any state, and then prove it must be what? In the subsequent state. So now my question is, now how do we analyze the code? How do we analyze the code? We ask what? What can change P4 and Q4, right? So question, execution of which statements can make this false? Only, can make it false. So only P3 and Q3. That's the only thing that can make it false, right? So let's analyze each one. Case 3. Now watch this. P3, okay, so now P3 executes, right? So P3 executes. By code, this implies by code inspection what? About want Q. No. By code inspection, what does that do to want Q? It makes it false. Is everybody with me on this? So P3 executes by code inspection, that makes want Q false. So we have not want Q. Is everybody with me on this? Okay. But now, what about not want Q? By lemma 4.3, what did we say lemma 4.3 was? Want Q equals what? Want Q equals what? Q 3.5. So what does this equal? Not what? Not Q 3.5. Is everybody with me on this? Okay, but what is the definition of Q 3.5? What's the definition of Q 3.5? Q3 or Q4 or Q5. And what's the not of or by De Morgan? And so what would this be? And not Q3 and not Q4 and not Q5. Let's go to the next slide. Not Q3 and not Q4 and not Q5. But what does this imply? It implies just one. Can't we use strengthening? Doesn't this imply just one of them? Which one do we want it to imply? So this implies by strengthening. Which one are we interested in? Okay, so not Q4. Is everybody with me on this? And now what about weakening? 3.76a. What can we introduce at this point? Or, yeah, we want to introduce a not or. Yeah, we want to do an or. So what do we want to do? What is it we're trying to find out? So not Q4. So by weakening 3.76a, we can introduce an or, a disjunction, a disjunct. Okay, so not P4 or not Q4. But then this by what? Is what?
Not P4
And not Q4. Oh my goodness. Is that not slick? You use all this stuff. I just think that's the cat's meow. All right, good deal. We'll close it there. See you next time.